Welcome back. In the previous modules, we looked at classical information and qubits. In this lecture, we will look at the gates, the quantum gates. How do we operate on those quantum states? We will only concern with single qubit gates, that is, applying operations only on a single qubit. And we will cover the topics reversibility and irreversibility, common 1 qubit gates, and general 1 qubit gate. So let's start. So, first of all, what is a quantum gate? As you remember from the classical paradigm, we have an initial state, let's say A, and a final state, let's say B, that we want to achieve from A. So we apply a gate in between them. Let's say this gate is U, which transforms this state A, let's say state psi, to a different state, let's say phi. So pretty simple. Quantum gate does what a classical gate does, but to qubits. But there must be some difference between a quantum gate and a classical gate. They should not be the same, or maybe they are. We'll see. Now, a reason to think why they might be different is because they are operating on a different system. We discussed how bits differ from qubits, therefore quantum gates must have some properties which, when it operates on a quantum state or a qubit, it preserves the nature of the qubit, right? Because if we operate on a qubit, we don't want a bit in return, we still want a qubit in return, right? So as you know from linear algebra, all the quantum mechanics is linear. That's why we are able to describe it with the help of linear algebra. The wave function psi is linear, which is described by like this, or the Schrodinger equation is also linear, and all the related things are linear. So the quantum gate which operates between these two states must also be linear. So that's our first property of a quantum gate, that it must be linear. And so the second property is that the quantum gate must be reversible. We'll discuss what each of these properties mean and what do they imply. But why must a quantum gate be reversible? The reason is simple, because there is a thing called the no cloning theorem in quantum mechanics or quantum information science, according to which no two qubit gates or no two quantum states can be the same in a given system. So we cannot obtain 0 0 and 0 0. They simply cannot coexist. They can't coexist. Therefore, if we operate, let's say the system is A is 0 0 and we operate a gate U, we cannot obtain 0 0 and 0 0. This thing must be something else, either 0 1 1 0 or 1 1. And this is only possible if this quantum gate is reversible, because if it is irreversible, it will repeat one of these. So that is the reasoning behind it being reversible. Now let's see an example. So this is an example of a quantum gate here. We denote the quantum gate simply by U, that's a convention, and we study how we study the action of a quantum gate is on its basis. So as you are familiar that we have been using 0 and 1 as our basis. So to determine what any quantum gate will do to a particular quantum state, so let's say like this, if we have particular quantum state psi, which is equals to, which we represent like this, because it is in a superposition of our basis vectors 0 and 1, we represent it like this. To study the action of any quantum gate on this state psi, let's say we apply a gate U, which is denoted like this in the Dirac notation. We apply this. So we must know the nature of how the gate applies on 0 and 1. So this would be simply like this. So all we need to study to know what the gate does to a system psi is what it does to our basis vectors 0 and 1, and that's how we describe a gate. It's similar to the truth table from the classical system. So just a quick reminder, in the classical system, if we have two qubits in the classical system, if we have two bits A and B, and we have to consider their output, let's say 0 0 1 0 0 1 1 1, and we get an output, let's say it's just an OR gate, so we get 0 and here we get 1 1 1. So we technically, in the classical system, we also study the action of the gate only on the basis, because superposition states do not exist. So to summarize, that's all we need. This is all we need. This is all we need. This is all we need. How the quantum gate acts on the basis vectors, and we should be able to describe what it does to any arbitrary state psi. Okay, let's move ahead. So this just describes the quantum gate must be linear, meaning we can distribute it across superposition. Implies is this statement, that is, it must preserve the total probability to be equal to 1, and we can simply follow this from this example, and we operate the above given state, this thing that we had, on a particular vector on an arbitrary psi. This is our arbitrary psi here. This is our arbitrary psi. We always represent it like this. This is how we linearly map it or linearly distribute it. That's what the book meant when it wanted to say distribute. Okay, so, and this follows from the property of linear algebra. That's why a quantum gate must be linear. So we can look at this and we can obtain the final state as this. So you see, we started with alpha and beta, and we end up with, let's say, they contain alpha beta, so I'll just say alpha dash and beta dash, but we end up with something of the format of alpha dash 0 plus beta dash 1. And now we know that the total probability must be equal to 1. Therefore, this alpha dash square plus beta dash square must be equal to 1. And this is what is done, where this thing is alpha dash, this thing is beta dash, and this is what has been done in this whole step. We prove that the total probability is conserved to be 1. You can follow these steps, it's quite trivial. Now, this is a further example of how the classical and quantum reversible gates look like. So this was an example of linearity. Now this is going more in deep into reversibility. So let's consider this classical gate 0 1, and when we input 1 we get 0. So as you must remember, these are unique or different, so therefore this is a reversible gate. However, this, which does not has unique outputs, no unique outputs, therefore this does not classify as a reversible gate. Any classical gate which is reversible can be used as a quantum gate. So if you remember from the first lecture, we made the AND gate, which is in classical information, reversible, and we named it Toffoli gate. My spelling might be wrong here, but it is called the Toffoli gate, or the CC0, if you are familiar with the quantum information. And this state, because it is reversible, can now be used as a quantum gate, and it is in fact widely used in quantum information. You will see it many times across. So this is a proof of why a gate must be reversible. We again try to prove that alpha square plus beta square must be equals to 1. This is a very important rule for quantum mechanics, that the total probability of observing a state must always be 1, and we obtain this here. And in this case we do not obtain 1, not equal to 1. That means that the gate is irreversible and cannot be used as a quantum gate. Okay, let's go ahead. Now we will see some common 1-qubit quantum gates. The very first one is the identity gate. It conserves 0 to being 0 and 1 to being 1. It is a classical reversible gate, the identity gate, so it keeps the states normalized and is a valid quantum gate, so does nothing. The poly X gate is basically the NOT gate, if you remember from classical information, which was written like this, but it is different. The difference comes on the basis. So this is the poly X gate. We'll discuss what it means, why is it different. If we just consider it normally, it is exactly the same. If we get an input 1, it gets it to 0. If we have 0, it gets it to 1. So it is exactly the same. The functioning is exactly the same. But we discussed last time the basis. So basis is nothing but the set of vectors which we choose our quantum state to be measured in. So for example, we are traditionally have been considering Z basis, right, for our measurement, and we'll continue to do that. What the poly X does is, as you can see in this diagram, rotates any given vector along the x-axis. So this is our classic swing. And here is the person sitting, and here is maybe another one, but you simply swing around this axis, right? So this child just swings back and forth along this axis. It's also like a simple pendulum. So the rotation of the axis of rotation here is this. This is the rotation of axis, right? And in our convention, this points in the y direction, but you can understand how this rotation is working. It's just rotating a quantum vector around the state. In this particular case, it is rotating along the x-axis, but we will further see other examples as well. So if we start with a quantum state, let's say here, this is our state 0, right? You know. Now what the quantum gate will do, what the poly X gate will do is rotate it along the x-axis. So this is our x-axis. It will rotate it here like this by 180 degrees or pi, angle pi, and we'll end up with this as the final state 1, which, if you remember, you see 0 goes to 1. So this is a very simple example. So let's say if we have x m number of times and it is operating on 0, we would get, if m is odd, let's write it here, if m is odd, we'll get back x0, because as you can see above on this, if m is even, we'll simply obtain nothing, or the identity gate which does nothing. Okay, now let's continue to the next one, because next gates, poly y and poly z, are pretty similar to this. It just changes the axis of rotation. So if we consider the poly y gate, it rotates any given state along the y-axis. So that's pretty simple. So what it will do to the 0 gate, which is here, it will rotate it along the y-axis, so by 180 degrees, and we will obtain the states as follows. Now this iota is an extra complex term here, because if you remember, we described this as iota and this as minus iota. This is definitely not a classical gate. We don't have iota and minus iota, but you can prove that it is a quantum gate by again proving that the total probability is 1. Therefore, it is a quantum gate. Now, let's consider another important thing here. If you have a quantum state along the axis of rotation, so if I say you take the state iota, now how would you rotate it along its own axis? So you can't rotate it, or even if you try to rotate it, it will rotate in itself and come back to its initial position, so it will remain iota. So therefore you cannot apply poly y, you can't apply poly y on iota or minus iota, because you can't rotate a state, or if you try to rotate a state, you will get back the same initial states. Similarly, for the poly x gate, you cannot apply, or if you apply, you will get the same thing to plus and minus gates, because they are on the x-axis itself. And similarly, for poly z gate, which we'll discuss in a minute, is quite trivial, and it is written here as well. You will just obtain 0 and 1 as it is back. You don't need to worry about this minus, because as we discussed in global phase, this is exactly the same thing as -1. When you want to represent it on a block sphere, 1 and -1 will both be represented like this. Okay, this is -1. I don't know why it got cut off. So this was poly x, y, and z gate, which was like the classical traditional NOT gates. Now we'll get to the next gate, the phase gates. So what the phase gates do are basically, you can think of it as they change the phase of the whole gate. Not the global phase, but the relative phase, because we know nothing happens from the global phase. So all the phase gates that we are going to discuss rotate similar to as the poly xyz gates. They rotate given quantum state, but what we are going to discuss, they will rotate about the x-axis. They will rotate around the z-axis. Sorry, they will rotate around the z-axis. You can create gates that, you can create phase gates that rotate along the x and y axis as well, similar to the process we'll discuss, but we'll just discuss the phase gates about this rotation about the z-axis in this module. The first one is the S gate, which is the square root of the Z gate, which means that it will rotate any given quantum state about the z-axis by pi by 2. So if this thing is here, and if we rotate it by pi by 2, we'll end up where we started with, right here. And even with 1, it will rotate where we started with, so back here. Now it doesn't do anything to the 0 and 1 gates, because as we discussed, they lie around the z-axis along which we are doing the rotation. We obtain the same states. You might think there is this iota here. What it is doing, it's just changing the phase. So if we consider the gate 1 and we apply z gate on this, obtain iota 1. Okay, let's see the probabilities. So how we compute probabilities is just by taking the amplitude, which is just 1 here, 1 square, so the probability is still 1. The probability here, is iota square, and then we mod it, which is -1 mod, which is 1. So the probability still remains the same. And this is the same also in the poly y. I forgot to mention, you see iota and minus iota as coefficients, but the states effectively remain what they are supposed to be, which is like the traditional NOT. So 0, if we start 0 from here, it becomes 1, and if we start from 1, it becomes 0. Those are just amplitudes. The probability remains the same. Those are just phases, so to say. Now, let's consider how will this gate act on plus. So plus, if you remember, is this, and we can write plus as this is along the x-axis, 1 by root 2, 0 plus 1. Okay, so we know that it will rotate it by 45 degrees along the z-axis. So we should expect something like it by 90 degrees, pi by 2. Currently it is pointing here. So finally it will point here. And you remember the state iota, and we will just going to prove it right now. Okay, so let's apply our S gate on plus. So we keep this as the same, we don't interfere this. We apply S on 0 and S on 1. This is because we can linearly distribute the gate. This is the property of a quantum gate, which we discussed earlier. And so this will become, so what does it do to S0? It does nothing, it remains 0. What does it do to 1? It attaches iota 1. And if you remember, this state is nothing but I. So we get the state that we expected to get. Right. This is just a further explanation. So if we apply S square twice, that is, let's say here we rotate it once and we rotate it twice, what we will get is the classical X gate or the poly Z gate. By X I meant not. We'll get the poly Z gate, that is the total rotation, like pi of 180 degrees, which is nothing but the poly Z gate. So this is what it describes. So the T gate rotates by pi by 4 or by 45 degrees along the Z axis. So again, if you remove this for a second, we get 0 just goes to 0 and 1 just remains 0, because again it's along the axis. But we need this phase to be considered, for example, when we try to transform something which is not along the z axis. So something like this vector plus, if you want to rotate this would come out to be somewhere in between here. Use a different color. Somewhere in between here. This angle is pi by 4, 45 degrees. And so t, if we apply t again, if we rotate it by, again we'll get, you remember the last thing, the S gate. So t square is S, and we know that S square is Z because we're along the Z axis. So this effectively, t raised to the power 4 effectively becomes Z. That's what it says, 4th root of the Z gate. Now, this is the Hadamard gate, one of the most important gates in quantum information, which we will see in almost every circuit. It is really important. What it does is transforms 0 into the plus state. So we start here on the Z axis with state 0, and when we rotate it along with the Hadamard gate, we obtain this state here, the plus state. What the Hadamard gate does is rotates any given state along this line x plus z. So it rotates by pi radians. So if we consider like this example here, 0, we start with here and we rotate along the x plus z by pi radians. So we obtained this plus state. And similarly for the one state, which if we start by here, we rotate it like this and we will obtain this state, the minus state here. And you can do the normalization easily. This is very trivial. So this is the key here. Now the Hadamard gate, we can further consider their action on the other states. So we had 6 bases or main 6 gates, 0, 1, plus, minus, iota, and minus iota. We looked what it does to 0, it transforms it to plus, or transforms it to minus, Now plus, it will transform it back to 0, minus, it will transform it back to 1. The proof of which is shown here. We take plus, we apply HADMOD, h0 becomes h plus, and 1 becomes, so here h0 becomes h, this is the plus state, and 1 becomes the minus state, which we know from here. And when you simplify it, you get back the 0 state. Similarly, you can prove it for this. What about the iota? So iota transforms to minus iota, and the state minus iota transforms to iota, the proof of which is given here. This and this you will do as exercises. This will be shown in the exercise, yes. And just as we discussed the poly XYZ gates, if you applied the gates twice, let's go back for a minute. Yeah, this should be good. If you apply the gates twice, so for example, yeah, if I start with a gate here, let's say, and you rotate it twice, so you rotate it once, you obtain this point right here. If you rotate it once again, you get back to the original starting position. This was plus, right? So y square is I. This was the poly z gate. So z square is I. Similarly for x square and y square. So you get the same states again. Similarly for the HADMOD gates. Why? Because it also rotates by pi, or 180 degrees. So when you rotate it twice, you get 360 degrees, which is nothing but 0. So you get back the same thing. So this is just that x square is equal to I. So these are the main basic 7 quantum gates, which are which does nothing, poly x, y, z gates, which rotate by pi by radians, pi radians along the respective axis. Then we had the S and the T gates, which rotate by along the Z axis. Let's write it here, Z axis, by pi by 2 and pi by 4 respectively, and the HADMOD gate, which rotates along the Z plus X, again by pi radians. Okay, so far we just used a single gate on any bit. So if we see here, we have a state, let's say A. Now we are studying quantum mechanics, we'll name them psi. We apply a gate U, so it's the convention, and we obtain a state phi, right? So we apply only one. This is just a simple example of applying these 4 gates together. So the order is from right to left, or whichever one. So we apply the HADMOD gate here first. So when we apply HADMOD gate, we know that HADMOD gate on 0 is 0 plus 1, and we normalize it 1 by root 2. So you simply follow the order of operations and you will obtain. So we are done with the HADMOD gate. Next we apply the T gate. We know what the T gate does. The 0 remains 0 and it adds a phase of pi by 4 to 1. Next we apply the S gate. We'll add a gate of pi by 2. So this pi by 4 plus this becomes 3 pi by 4. And the last gate is again HADMOD. What HADMOD does to 0 and what it does to 1, the phase being remains same. And this is what we obtain as a final gate. So multiple gates is quite simple. We apply one gate and then the next gate. We apply one gate, then the next gate, then the next gate, and the next gate. If we try to measure the state in the Z basis, our favorite, we will just take the square of the amplitudes, and here's where we can get the amplitude. It's quite trivial for this and for this. So this is the main thing about quantum gates. We discussed 7 main gates, and then how can you apply them in an order, multiple gates. This is now we will see the generalized one qubit gate. So for example, you have any gate u, any random gate. So what, like the one that we considered in the start, for example, this particular gate. This is a random gate. We didn't name that gate. It does some random manipulation to the bit 0 and 1. We can represent this random gate u as in the form of I, X, Y, and Z. So we don't know what this u does, but we can transform this u gate so it is simply represented by I, X, Y, and Z. I won't go much into the detail because it is not relevant for this course at this moment, but you can simply see how it is done. This n hat is the axis of rotation. We'll see an example, and then you simply apply this formula. This, you don't need to worry about this. This is just the global phase. You can ignore it. And this must be a unit vector. This is the important thing, and you just plug into the formula. And theta is nothing but the axis, the angle of rotation. So by what angle do we rotate a particular quantum state? For example, the Hadamard gate, we know it rotates along the x plus z axis by 180 degrees or pi radians. So our n is simply the axis of rotation, so we know it will be x plus z hat, and we rotate it along this axis. So we write it simply like this, and 1 by root 2 is just the normalization factor. This must be 1. We have theta equals to pi, the axis of the angle of rotation, and we simply plug it into the equation, and we obtain it in this form. So Hadamard, which was a random gate u, can be expressed in our simple gates as x and z, or x plus z and some normalization factors. Let's see how this works. We apply this gate, a newly formed gate, on the state 0, and as expected we obtain plus. Remember that Hadamard acting on 0 gives us plus, and acting on 1 gives us minus. So we obtain the same thing. Right. You can also use this to prove that rotations are linear. That is the fundamental property of quantum gates. We won't go into the details, but you can look at this proof. So this is the end of our module, and now we have some exercises. These are some questions that you can try, and you can ask me if you have any doubts in the office hours. And this is quite a good example. This question is quite good to test like your overall understanding, especially of this concept of the generalized one qubit